Hello, my name is Gagan, and this is my discussion for miscellaneous algorithm module for advanced algorithm unit. So firstly, I'm going to go through the taxi problem. What is taxi problem? So we have a taxi and we can make 6 moves up, down, left, right. There's some walls in the environment, and our aim is to pick up the passenger and drop it off. So picking up the passenger and dropping off gives us a reward, and we're going to use that reward to train our model later. Firstly, let's compare a random solution to what we're going to do later. So let's show what will happen if we just make a bunch of random moves. As expected, nothing is going to happen. The taxi is just moving randomly with no aim, and the passenger is not picking up, and so many moves are wasted. I'm going to stop it here. So let's compare it to the reinforcement learning based solution, which uses Q learning. And in Q learning, we use a Q table. And in this Q table, the Q table has dimension of the number of states and the number of action. And each state action pair will have a Q value associated with it. And we are going to use the Q values to make moves. So I already trained the model for 100,000 iterations. And this is, as you can see, the updating of the value uses the reward that we get from taking the action. And we're gonna there's also some concept of exploration and exploitation. Sorry. So 10% of the time, which is epsilon, 10% of the time we're going to make a random move, and the other 90% of the time we're going to choose the action from the action state from the Q table. So for updating the value, we're also using alpha, which is like learning rate. So how much importance you want to give to the current state and the current value and the learned value. So I already trained it. Quickly going through it again. So we run it for the number of episodes. We're going to keep updating Q value using the Bellman equation, and in the end we'll have a Q table filled with values, which will give us the optimal working for the taxi problem. So let's run it for 10 episodes and let's see what happens. So as seen from the simulation, it's very efficient in picking up the passenger and dropping off into the drop-off point. So the model has learned how to play this game. And if we do some evaluation on it, we can see that the average episode takes 12.95 steps, and there's no penalty in any of steps. So that model has learned really well to play this game. Now moving on to before moving on to MapReduce, I want to talk about the other variant of that is present in the module, which is deep Q learning. So what deep Q learning is instead of using a Q table to obtain the actions and pass in the state, we are going to use a deep neural network. And what the deep neural network will do is we're going to pass the network the state data, and it will give us the action. In the beginning, it's not going to be really good, and as the weights will be all random. So we need to have a loss function which we're going to use to minimize, and for that we need to have we have to compare it to the actual value. But since this is not a supervised type of learning, we don't have any actual values. So what we're gonna use is, for the actual value, we're gonna again pass the next state we are reached in. After taking the action, will be in a next state, and we're gonna pass that state into the deep neural network, and whatever we're gonna get as output, we're going to use that as the actual value, as if that is the actual value, and we're going to add a reward to it first. So in the beginning, it's not going to be really good. It's going to be it's going to look all random, but After some number of iterations of time, since we are adding the reward, the states that which leads to rewards will be preferred, as the weights will be changed according to those rewards. So we are passing in the state whenever that state is becoming we're getting more getting to the states that will give us rewards. So we're going to pass that. So the reward is going to help in changing the weights of the neural network, and hence the whole Q table can be replaced with the deep neural network. And it is very helpful when we have a large number of states which are not possible to like store and manage in using a simple computer. So we will run out of memory. For example, in chess or in AlphaGo, we use we can't use a table to keep track of the state, and there's a lot of action, so it's going to be way too much memory. So now moving on to MapReduce. What is MapReduce? So it is a way of running parallel computations by splitting the algorithm into two parts: map and reduce. So what we have, if we have a cluster of computer which are connected to each other, which are not connected to each other, which are running their own, which can run their own calculation, and some of them are mappers, some of them are reducers. So what we'll do is we're going to split our algorithm into two parts so that it will have a mapping aspect and a reducing aspect. So for example, I have three examples in here which I will demonstrate to show the point. So firstly, we're going to go through word count. In word count, we'll store a key value pair for documents, but we're not going to give one computer all the documents. Instead, we're going to split the documents, and we are going to give the documents chunks of documents to the computer, and each computer will be running the map, and it's going to count how many words are there in those documents. So as you can imagine, when there's a bunch of computers running those algorithms, instead of counting one document, we can count k documents if we have k computers. So it's going to reduce our time by k. It's going to increase our computational power by a factor of k for k computers. And what the reducer does is that it's going to aggregate all the values that we got from the mappers, and it's going to add them. It's going to make a key value pair for those one, and those will be our final values. For example, in this, we have, if we look up the word that from the reducer is 177, but in the individual articles is 79 and 98, so it added them up. Now I'm going to do matrix multiplication using MapReduce. So how matrix multiplication is done? For example, if we have two matrices M and N, we multiply the row and a column of the second. So row of M, column of N. So this is how we're going to store those this is just giving the first mapper will give us a way to represent the row column so that it can be multiplied later in the next step. So how what it does is that for matrix M, we're going to go through the rows, and for each row we're going to look up the value, and we're going to store that value alongside the row and the indicator, and the key for this key value pair will be the column value for M matrix, and for N matrix the key will be the row value. So then we're going to iterate over rows, then we're going to get the values, and we're going to have a key value pair as such. So in this one we have column, and this one we have row, and then we're going to send it to reducer one. So I'll show you the examples as we go. So this is what it'll look like after running the first map. And then what the reducer 2 does is that it multiplies the corresponding value. We know that each row the first element will be multiplied by the first element of the column for each column. So it's gonna be like first element of M will be multiplied by the first element of the first column, the first element of the second column, and so on. So this is where what is going to happen. So we're going to check again the row column relationship that is at the core of matrix multiplication, and we're going to store the row column which the inverse of what it was. So in previously we had rows for matrix M. So it's going to be column for matrix M, and the other way around. So we're going to multiply those values here, and then we're going to return these values. So running this will look like something like that, like this. So it's just a multiplication of each different element possible. Now next is the second mapper. So this is just for identity, and this is just I'm using it for formatting. The formatting the key for which will be used in the next one. So what next one is a reducer. So second reducer. So this is in matrix multiplication. We after multiplying the row column, and we are also adding all the elements to get the final element. So this is what this step is. So wherever the identity is same, it's going to add those values. So yeah, as you can see, it's going to make a key value pair. So we're going to run it. If it's not there, we're just going to keep adding those values. And after running that, we can see this is what we get. So at row 1, the value should be 22, and the row 1, 2, 21, and so on, so on. And this is the comparing it with the numpy dot product. And you can see all the values are same, so the function is working properly. We can run it using running again. Another test case. This is for 3. And the final one compare with the dot product. Now, the final equation that I'm going to talk about is page rank. So what is the goal of page rank? The goal of page rank is to rank the pages which can be used to have them show up properly in a search engine whenever you search for it. So I'm representing the pages as such. So the first letter will be the page itself, and whatever the next one, whatever comes next will be the links which the page will contain. So for example, A has the links B and C and so on. So first step is we initialize a rank. Each rank will be 1 divided by the number of total pages we have. So in this case, we had 4 pages, so we're going to have 0.525 each. So in mapper, what we are going to do is that we're going to calculate a vote. What is the vote? So it will be the rank of the page divided by how many links it contains. And for every single adjacent it has, we're going to give that, create a new key value pair, which will be that page and what vote we give it. So for example, in this case, it will look like this. So this came from page A, because page A had B and C, and 2 0.25 got split into two, 0.125 and 0.125 and so on. And then we are going to do reduce. What a reduce does is it's going to look up at every single key value pair, and it's going to see whenever the key is equal. So for example, this one has two C's in it, so it's going to add up these values. So it's going to aggregate all the key values pair into our final result. For example, this is what we're getting for this example. When I run it another example, so in this case, notice that every link has C in it. So B has C, A has C, B has C, C cannot have C because it is C, and D, A, let's add C in here. And that's it. So I'm going to run it with this. As you can see, that the rank for C is quite high, which is lower than B. So B must be, there's a B here, there's a B here, B here, and B here. So if we like change it in a way, for example, I want the B rank to be somewhere. So I'm going to remove this C. Let's remove this C as well. Let's connect, yeah, B, B, and B. Yeah, so again, if I run it, we can see that B has the maximum rank. So B is connected to most of the pages in this example. That's it. Thank you.